Determine whether the planes are parallel, orthogonal, or neither. If they are neither parallel nor orthogonal, find the angle between them. We are given two equations of planes. The first equation for the first plane is given as 3x minus y plus 2z is equal to 2. The normal vector for this plane, which I'll call this plane, plane 1, a normal vector that can describe this plane is given by 3 minus 1 and 2. A second equation describes a second plane. So the second plane is given by the equation 2x plus 3y plus z is equal to 4. And a normal vector that can be used to describe this plane has components 2, 3, 1. We have to determine whether or not these planes are parallel, if they're orthogonal, or if they're neither. If the planes are parallel, then we should be able to use a cross product to determine that. If the cross product is not 0, then we know that there is some angle between the normal vectors, which means that the planes will intersect along a line of intersection. So our goal is to see whether or not they're parallel first, or at least I'm going to determine whether or not they're parallel first, because I know how to do that test pretty easily by taking the cross product between the two planes. So we will say test for parallel normal vectors. And that test will be given as the cross product between the two normal vectors, and we want to know if that cross product ends up evaluating to 0. If it doesn't evaluate to 0, then we know that the two planes will intersect along a line. Let's construct our cross product. So the cross product between planes 1 and 2 is given by, and I'm going to do it using the 5x3 matrix technique. So we have columns given by their respective components. So for the first normal vector, we have components of 3 minus 1, 2, 3 minus 1. And for the second vector, this will be in the third row. The second vector has components 2, 3, 1, 2, 3. We will take products that are diagonally down and to the right and subtract products that are diagonally down and to the left. When we do that, we have the cross product between the two planes is given as, and we're going to have an x, y, and z component. So the x component is going to be given by the product of minus 1 times 1. I am looking down the x direction, or the x hat diagonal. And then we are going to subtract the I hat diagonal in the opposite direction. So that's going to be the product 2 times 3. That is the x component. For the y component, we have the product 2 times 2 down that diagonal. And then the opposite diagonal, we have the product 3 times 1, which we're going to subtract that from 2 by 2. And for the z component, looking down the z diagonal that goes to the right, that is the product 3 times 3 minus the z diagonal that goes down to the left. So that is minus a minus 1 times 2 for the z component. This becomes now the cross product between those two normal vectors is equal to minus 1 minus 6 for the x component, 4 minus 3 for the y component, 9 plus 2 for the z component. I can see already without evaluating this, and really I've known from this line that the planes are not parallel. The reason why I know the planes are not parallel, it's because we have at least one non-zero component to this cross product. And in fact, none of the components are equal to 0. However, we only need one component to not be equal to 0 to say that these planes are not parallel. Since this cross product is equal to the 0 vector, we know the planes must intersect along some line. So we have just used the dot product, or rather the cross product, to show that the planes are not parallel. So now let's figure out if the planes are orthogonal. If two planes are orthogonal, and let's just illustrate two orthogonal planes. This is plane 1, and here is plane 2. Plane 1 has a normal vector n1. Plane 2 has a normal vector n2. These two planes are orthogonal if their normal vectors are perpendicular. And we know that if the dot product between two vectors is equal to 0, then the vectors are perpendicular. And for these two planes, if they're perpendicular, they will intersect along a line of intersection. Really, all we need is that the planes are not parallel for them to intersect along a line of intersection. So let's figure out what the dot product between planes 1 and 2 are. So the first normal vector has components 3, minus 1, and 2. And we're going to dot that first normal vector with the second normal vector that has components 2, 3, and 1. When we evaluate the dot product, that is going to be the sum of the products of the components. So the product of the x component is 3 times 2. Add it to the product of the y component, which is minus 1 times 3. Add it to the product of the z component, which is 2 times 1. The dot product is 6 minus 3 plus 2, which evaluates to 5. Well, the dot product between these two normal vectors does not equal to 0. That means the planes are not orthogonal. So we'll say, therefore, not orthogonal. For those planes to be orthogonal, we would have ended up with a dot product equal to 0, which that's not what we have here. We have a dot product equal to 5. We now know that the planes are neither parallel nor orthogonal. Let's sketch a representative sketch to illustrate the angle between the two planes. And actually, let me start the sketch over. I want to exaggerate the angle. So let's say we have a plane that looks like this, and let's say we have a plane that looks like this. Those two planes are clearly not perpendicular. They are clearly not parallel. They are at an angle with their normal vectors are at some angle relative to each other. And these two planes again intersect along a line. To find the angle between these two planes, we could use the dot product for that. We could also use the cross product for that if we wanted to. Since we've evaluated the dot product, let's use that. The dot product between these two planes is equal to 5. But remember, a dot product is defined as the product of the magnitudes of two vectors times the cosine of the angle between those two vectors. So between these two planes that I drew, and by no means am I suggesting that our actual planes have this orientation, my sketches are used just to get a qualitative sense for what to do on the problem. These two planes, their normal vectors would have an angle between them. We can use the dot product to figure that out. So the product of the magnitudes of both normal vectors times the cosine of the angle between them must be equal to 5. This means the cosine of the angle between those two normal vectors is equal to 5 divided by the product of their magnitudes. So the cosine of the angle between those two planes is given by 5 in the numerator, but let's look at the denominator. The denominator is the product of the magnitudes of the components of those two normal vectors. So for the magnitude of the first normal vector, we have 3 squared plus a minus 1 squared plus 2 squared. The magnitude of the second normal vector is 2 squared plus 3 squared plus 1 squared. This means that the cosine of the angle between those two planes is given as the square root. Let me see if I could do this in my head. 9 plus 1 is 10, plus 4 is 14, times 4 plus 9 is 13, plus 1 is, wow, we got lucky on this problem. Let me see if I did that right. 3 squared is 9. 9 plus minus 1 squared is 10, plus 4 is 14. And 2 squared is 4, plus 9 is 13, plus 1 is 14. Oh, we got lucky because I don't need my calculator. I was worried I might need it to do some simple multiplication. But this ends up being just 5 over 14. Since the cosine of the angle between those two planes is equal to 5 over 14, if we take the inverse cosine on both sides of the equality, we end up with the inverse cosine of 5 over 14 being the angle. This is our exact answer, but let's see what that answer is in degrees. in degrees, when I put this into my calculator, I'm putting in the inverse cosine of 5 divided by 14, and this ends up being 69 degrees. And to the nearest tenth, that is 69.1 degrees, is the angle between the two planes.